Hello, and welcome to Microsoft Research Summit 2021. This is our talk on the state and future of software supply chain security. My name is Adrian Diglio, and I'm joined here with my colleague, Michael Scovetta. First, we're going to start out with a quick disclaimer. This talk and accompanying slides are for general information purposes only and are not intended to constitute legal and professional advice. A little bit about myself. I'm Adrian Diglio. I'm a program manager inside Microsoft that is leading the central strategy to secure our software supply chain. I've been at panelist discussions before with other industry peers, both with U.S. Department of Energy and with North Carolina State University. I've got my bachelorette from Cal Poly and my master's from SDSU and some industry certifications.
And I'm Mike Scovetta. I'm a principal at Microsoft. I lead an open source security team. Our goal is to make sure that Microsoft is protected from vulnerable or dangerous open source software. I also lead a work group within the Open Source Security Foundation, and I have a master's from Cornell in computer science and a CISP.
And so in our talk today, we're going to cover two topics. First, Mike is going to talk about what software supply chains are and why we need to help secure them. And then I'll come back and talk about how Microsoft thinks about this problem and our approach for managing the risks. Over to you, Mike.
Thanks, Adrian. So modern software is practically never built in isolation. We all stand on the shoulder of giants, with those giants being other software components, libraries, services, hardware that we use to help deliver products that delight our customers. A software supply chain is really this collection and the interaction of everything that goes into delivering your product, your software product or your service. It includes things like third-party vendors, like the software that you get from Microsoft, the external service providers, whether it's a cloud service provider like Microsoft or Amazon or Google, source code repositories like GitHub, and everything else that you don't have to write yourself, that you leverage someone else's work. But it also includes things like the laptops and the other hardware that your developers use and how they interact with systems that they're building. It includes the distribution channel to customers, how you actually get your service in front of the users, including things that you wouldn't normally think about, like their internet service providers. The software supply chain has been around for as long as software has, but in the past 15 or 20 years, there's been a seismic shift. One of the reasons for this shift is a very large and increasing reliance on open source software. In fact, the average software application now depends on over 500 different open source libraries, according to a report from Sonatype. There's increasing complexity. Many times these open source components depend on yet other open source components. There's more parties involved. So if you are one of these applications that have 500 different open source dependencies, these are at least hundreds of different people that are contributing to your service that you've never met, that you have no relationship with. There are also inherent adversary advantages. When an attacker tries to compromise a software supply chain, they can, especially when it's around open source, they can do this in isolation and analyze for days or weeks before mounting an attack. And when they do attack, the payoff is higher. The average ransomware attack is close to $600,000 from another recent report. So this has been in the news. It's been in the news for years. I think what's changed in the past few have been that attackers are now targeting critical systems. So two recent breaches or attempted breaches. One was the attempted attack on Florida's water system. And the other was the successful Colonial Pipeline breach. These had, particularly the Colonial Pipeline breach, had massive impact. SolarWinds is another good example. SolarWinds is interesting because it didn't target traditional. It didn't have a traditional target. It targeted build systems. This has all kind of culminated in the realization that software supply chain is critically important to organizations and countries. So we see some movement happening federally with the recent executive orders on improving supply chains, and lots of other legislation and things that are coming to make sure that organizations mitigate this risk sufficiently. So let's think about open source software development in particular. And in a lot of ways, this mirrors any other software development. But consider, if you take an open source project that someone built and maintained, you can kind of bucketize the risk into a couple different categories. One is the risks that take place locally when they're writing their code on their own laptop. And then when they're done, they publish this to a package repository and they make it available for the world to use. And then you, being an organization that's using this package, downloads it. And then you use it in your application. You ship it in a service or put it on a download or anything like that. And at each of these areas, there are threats and risks that can come in to compromise the supply chain. And remember, you only really need one compromise of any of these things can impact the final service that you're delivering to your users. So attacks against in these areas have been prevalent for years. A few recent ones, though. So co-maintainer is attacker. Is kind of the way that we describe cases where you, as a maintainer of an open source component, you're busy. Someone comes along and says, "Hey, can I help you out? I'd love to partner with you and maintain this." This happened in 2018 when there was the event stream NPM project was compromised this way with an attacker coming in and asking to help. The maintainer gave them access, and the maintainer quickly added a malicious subdependency to that package, and chaos kind of ensued. Compromised credentials happen all the time, and in many cases, this is particularly prevalent in package managers where you could publish something to NPM or to PyPy or NuGet or another package ecosystem, and you lose those credentials. You lose a publishing token or something like that. An attacker finds it and publishes a new version of the package that has malware or something else kind of evil in it. And I haven't even talked about regular vulnerabilities, but regular vulnerabilities are everywhere because humans write software and humans make mistakes, and some of those mistakes are security vulnerabilities. But the problem here isn't so much this single thread of threats, but it's the way that these things kind of stitch together. Because remember, open source depends on other open source, and your software depends on third parties. The entire your entire graph of dependencies can impact the final your final service. So imagine that we just zoom in on here, and let's take this one in the middle, the compromised tool chain. So the example, the scenario here is you use a compiler and some sort of a build tool to create your package. Well, that tool chain is software too. So that was delivered to you at the end of someone else's flow here that I'm describing. And even there, that software was written on hardware that has software running on it, which was written by yet other people. So it almost seems kind of fractal in nature, where you can zoom in really, really far, and you realize that the simple web application that you're developing, it doesn't depend on dozens. It depends on thousands of people that are all making mistakes sometimes, and all can be compromised to deliver your final thing. So while the attack surface is enormous and it's enough to keep a lot of people like me up at night, you still need to ship software. You can't just be paralyzed by this risk. You have to ship something. And for that, I'm going to leave this to Adrian to talk to you about Microsoft's approach here.
Thank you, Michael. Now that we have that context, I want us to begin dissecting the problem into various segments and start to review Microsoft's solution approach. We'll try to tackle the full breadth of the problem, highlighting hard technical problems as we go, and we'll start digging in. At Microsoft, we have a complex, heterogeneous environment. We have over 100,000 developers. So as we approach this problem, I'm gonna use some basic examples, such as Azure DevOps. Azure DevOps is a well-known DevOps CI/CD platform, and there is such a large attack surface when you look at all the touch points across the CI/CD infrastructure. Some threats here can be performed by external attackers, such as malicious OSS packages and plugins, but most threats represented on this slide are actions that can be performed by an adversary that has already gained initial access to the engineering system. This is why the assume breach mindset is so important when developing solutions to this space. When we look across the landscape today, lower sophistication attacks such as code cov, dependency confusion, and typo squatting are much more frequent and more successful. These attacks techniques target developers' dependencies that get pulled into a build environment, such as open source software, build tools, compilers, linkers, and SDKs. Usually when the objective of the attacker is to compromise the developer's workstation or exfiltrate build environment credentials to an attacker-controlled server. This would grant the attacker initial access to our engineering systems, which is in that compromise workflow down below, depicting the cyber attack chain. And once they have this initial access to our engineering systems, that's when they start to pivot and escalate permissions within the environment until they can act on their ultimate objective, which is in the post-compromise phase, depicted below. And that acting on objective potentially is where they're targeting our build machines or searching for secrets in source to then go compromise our production services. There is also a potential threat that any of these lower sophistication attacks could execute ransomware in our environment, halting Microsoft's ability to develop software. When we look at these high sophistication attacks, SolarWinds in 2020, ASUS Live Update in 2019, and CCleaner in 2017, they show how devastating a supply chain attack can be for a company's reputation and customer base. The above attacks were performed by highly sophisticated adversaries that all targeted the build machine, with the objective of compromising the software produced to use the company's software as a vehicle to distribute their backdoor or malware, and it abuses the trust that these companies have established with their respective customers to ensure that the malicious payload gets executed. If our products were successfully compromised in this way, it would result in immediate and possibly irrevocable loss of our reputation. And that's why Microsoft is so committed and focused on this problem. So, defining the problem, where does it begin and end? Michael already took you through some of these thoughts, but it kind of begins that first moment that a developer starts writing code. They choose which IDE that they want to develop in, which OS is it running on top of, and all the software that gets brought into that developer machine, and ultimately into the project that's being developed. I would like to say that the supply chain ends when a piece of software is successfully and securely delivered to the customer. But if an attacker exploits a vulnerability that you inherited from a piece of OSS that you took a dependency on, isn't that still attacking your supply chain? So delivering it to the customer is not necessarily the end. It's kind of an ever-going evolution of continuously protecting your supply chain. And securing the supply chain kind of goes beyond secure development lifecycle practices and goes beyond DevSecOps practices, though practices from both of those disciplines often overlap and do provide benefits toward securing your supply chain. But there is more that needs to be done. When you look at this system, this is just a generic picture of the evolution of software going through modern day CI/CD. Something new that you might be noticing here is that evidence store depicted on the bottom. More on that later. So our strategy is to segment this into bite-sized chunks. We are taking a threat-based approach, focusing on reducing risk at each one of these segments of our supply chain, because we need to be able to validate our software development process and validate that our build output is free of anomalous or illicit activity. These 7 sections that I have here are build environment, OSS supply chain, build tool supply chain, securing the DevOps platform itself, securing the developer workstation environment, talking about how we can secure the upstream, meaning all of the things that we consume from, and ultimately SBOMs and supply chain integrity evidence. As I progress through, you will see depictions in the bottom right-hand corner of the slide, as well as numbers in the top of the slide, so that you know which segment we're referring to. So, to me, because these highly sophisticated attackers are our largest threat in securing the supply chain, focusing on build machines is critical. Microsoft's build machines should have secure boot capabilities to protect them from firmware rootkits, bootkits, kernel rootkits, and driver rootkits. All of the major supply chain attacks, SolarWinds, ASUS Live Update, CCleaner, they were all done by very sophisticated adversaries that all targeted the build machine. Compromising the boot process in order to get access to the build machine is something that these adversaries could do, are very capable of doing, and I want to be able to block that attack vector entirely to protect our software supply chain. Furthermore, on all of the different things that we can do to secure the build environment itself, Google released Salsa, which is a maturity model for supply chain security. Shown here are just the build-related items out of all of the others. As you can see in Salsa Level 3, they recommend ephemeral build environments where the build machine is there to perform its task and then it's blown away when you're done using it, so that attackers have no opportunity to maintain persistence in your environment. And also in Level 3, they talk about network isolation, because there should be no reason to have access to the public internet during a build. This is how attackers often call back to the command and control servers to download a payload, or in the case of ingesting compromised scripts that might exfiltrate your secrets to a remote server. If you've got network isolation in place in your build environment, those scripts will run, but they won't actually exfil anything. At Microsoft, we're going a bit beyond Salsa. One example is security monitoring of the build environment and looking at activity that's happening there. Another example is applying code integrity policies to the build environment so that only signed trusted binaries are allowed to execute in a build environment, which would have prevented the CCleaner attack, because in that specific scenario, they loaded a compromised DLL into the environment. OWASP also has the software component verification standard, which is much more granular in terms of requirements for its maturity model, and it's another great guidepost here that anybody can adopt. And then after a build, once we produce the output, how do we go back and efficiently walk backwards to the original artifacts that created and make sure that what we produce is what we expected to produce? This is essentially asking the question, how can we reproducibly validate? And this is hard for a number of reasons. Many languages have non-deterministic builds. There are date timestamp issues that are happening in certain build environments. Even minor changes in build tools could have significant changes on the build output, like compiler flags, so on and so forth. And sometimes source information is lost in between stages. We have here a few solutions that we're pursuing, reducing the amount of non-determinism during our builds, emphasizing declarative ephemeral build environments, so on and so forth, participating in reproduciblebuilds.org where we can. There are lots of opportunities for improvements in this space. Moving on to the OSS supply chain bucket, the program that we have running inside Microsoft is essentially a set of 8 practices. We want to make sure that you're ingesting and saving a local copy of the artifact, that you're inventorying that artifact, that you are scanning for vulnerabilities and malware, that you are updating in a very timely fashion. We measure mean time to remediate, and we try to use technologies like Dependabot to help automate patching. We also have audit, verifying the provenance and integrity of those artifacts as we consume them through the chain. And we also want to be able to ultimately enforce these policies on enforcing secure consumption. Because if people are able to pull things from any location anywhere, it's possible that they can mess up or accidentally pull in something that they didn't intend, and so establishing a ingestion gates that evaluate these packages upon consumption to block the bad and let through the good is a big part of securing our supply chain. Additionally, being able to rebuild from source where it makes sense, so that in extreme situations, if you uncover a critical vulnerability, you can be able to implement a private fix, rebuild it, and distribute it while you partner with the upstream maintainer and wait for them to make the fix. And so you can't do all 8 practices right from the get-go. You need to do them in phases. And this is where I get to the maturity model. And you can walk through this level 1, basic ingestion, inventorying, scanning for known vulnerabilities, and manual updating. Moving to secure ingestion to protect you from dependency confusion, scanning for malware, automatic OSS updates like with technology like Dependabot, and moving over to level 3, where you're actually cloning the OSS source locally so that you can perform proactive security reviews and look for those backdoors and other unknown vulnerabilities, and being able to contribute your findings back to the upstream maintainer. And ultimately, level 4. This is where there's a lot of subtle, hard technical problems when it comes to rebuilding and implementing private fixes. Rebuilding is actually tougher than it sounds due to non-determinism. And the reason why we would be motivated to rebuild OSS is because it's often done in a black box. Developers can build on their local desktops, they can introduce new scripts or dependencies that aren't found in their repo, or they could be building in a compromised environment. So while reproducibly rebuilding is a little bit out of reach for some languages like JavaScript, we have published a NuGet that does help you establish settings to support reproducibility for NuGet packages. But organizations that want to rebuild OSS on trusted infrastructure, this is a hard problem. You could produce a functionally equivalent rebuild, but it won't be a bit-for-bit hash match. Also, when you start thinking about private fixes, this is also very tricky, because if you implement a private fix, do you rev the version number with semantic versioning? Well, you can't really do that because the upstream maintainer is going to rev their version number, and you don't want to conflict. So then do you rename the package? And then how do you make sure that all of your developers across your organization get this renamed package? So these are all the subtle, hard problems that we are tackling now. And so with software build dependencies, this is the third step of pulling in, build tools and SDKs, things that could be coming from all over the internet. This is really an exercise in reducing our attackable surface and removing our reliance on the public internet. So we want to host an internal store where we can start pulling down these binaries and hosting them in a secure location where they can be vetted and reviewed and approved for use. And then all developers can start pulling from this internal storage location rather than constantly calling and making outbound calls. This is something that we're piloting. We are working on adapting a version of the relative attack surface quotient, which was initially created to measure the attack surface of an operating system. We're looking to adapt that formula and apply it to a build environment so that we can calculate the total attackable surface prior to implementing these things, and then measuring it as it goes down over time as we gain adoption in these new tools and standard best practices. DevOps platform security. This is getting back to using Azure DevOps as an example. Identity for years now has become the new perimeter. Protecting credentials is paramount to protecting your castle. This is why MFA is a must in this day and age. Additionally, we found that attackers that do gain that initial access, they still comb through repos looking for hard-coded secrets so they can pivot and compromise a production service. This is why highly recommend having no hard-coded secrets in your code, And the easier that we can make this for developers, the better. Thus, under this assume breach mindset, we need to establish secure baselines of all of the configurations that our builds are taking for our code bases and our pipelines. We should have two-person review on all the changes as a mitigation against malicious edits. Because if a person is in there and they want to add their little malicious build step, we need to make sure that we have humans monitoring that as a first step in mitigating this. Anything that requires admin level permissions, we need just-in-time elevation of permissions to do that, so that we have no account with persistent admin permissions. And we also want to encourage teams to take that threat model concept, which is traditionally done looking at the production service, and rethink that and have the threat model done on the build environment itself, so that you understand all of the inputs that are going into the build, and it forces development teams to think about it in a new way. Developer workstation security is another important, it's kind of like the first line of defense in many ways, because developer workstations are usually also connected to the internet and they receive email. One wrong click and the developer's credentials are compromised. This would grant an attacker access to anything that's been pulled to this local desktop. And as you can imagine, a lot of developers will do a clone of the source code from this highly secure, version control system and pull it down to their desktop. So it's going from like one security boundary into another, which is considered a little bit less secure. And, that clone source is intellectual property, and it's now low-hanging fruit. So if an attacker does compromise that credential, they can easily get what's locally there, and they can easily exfil that code and potentially sell it for ransom. And we've seen that a couple times in the news. And so for the next thing, Mike, I want you to tell us about how we can all be a better member of the security community.
Thanks, Adrian. So we all depend on open source extensively. I think that's just a reality of modern development. Our goal in this kind of part of the process is to have some sort of assurance that the open source and third-party software that we depend on actually is free from vulnerabilities. So this is different than being free from known CVEs or having integrity validated from point A to point B or things like this. This is actually opening up the code and looking at it and saying, are there vulnerabilities here that aren't public? Are there backdoors? Has malware been inserted? And how do we do this at scale relative to the number of projects that are in use? So Microsoft is, while we are a large organization, this is not a Microsoft problem. This is a problem for the entire world. So to help address this, we helped to create the Open Source Security Foundation, which is a industry organization, designed to kind of address this problem at scale for the entire open source ecosystem. There are a number of different work groups involved in this, and we're all targeting different areas and trying to improve things. If you're interested in this, we welcome participation from industry and organizations and anybody who cares about this and wants to help them make the world a better place. Back to you, Adrian.
And so here, this is the evidence store that I alluded to a while back. SCIM, Supply Chain Integrity Model, is our open specification on how to capture policy, such as REGO from OPA, and evidence that proves that you've complied with the policy in a single, immutable, non-repudiable supply chain integrity ledger. SCIM becomes the evidence store that enables software to prove that it meets, say, SALSA Level 2, as an example. And SBOMs come into the picture because of their unique software identifier that they contain. SBOMs contain much more information and serve software integrity and software transparency benefits as well, but they also cater to serving as the software identifier. This is poised to even potentially replace CPEs, which is how vulnerabilities are mapped to a software today. And so the software ID could be used as the lookup key in a SCIM evidence store to validate that any supply chain integrity evidence about the software. And so what does success look like in the future? Our vision is that in software supply chain security, we must be able to convey trust in Microsoft's software and its supply chain dependencies to our customers, which is a tall order. This is going to be accomplished through building our software in a verifiable, trusted build environment using a verifiable, trusted chain of OSS and build tool dependencies, each also built in a verifiable, trusted build environment, and recording this evidence as proof for anyone to validate in an immutable, non-repudiable evidence store. So thank you for your time and attention today.